Welcome everybody to this PSDI webinar. So I'm Dr. Nicola Knight, the PSDI coordinator, and I'm going to be here just to facilitate this webinar today. So this is one of our Pathfinder webinars. So today we are going to be hearing about some of the initial activities that are going on in PSDI and some of the development that's going on in those. Today's webinar is going to be presented by Alin, Elena and Federica from Daresbury Laboratories, a part of STFC. And so they are going to be talking about data to knowledge and then to data again. So without further ado, I'm going to hand over to you, Alin and Federica.
Okay. Hello. We will have a double act this webinar. I will start. I'm Alin Elena, and then somewhere in the middle, Federica will take over. Okay. So. What we're going to talk about, data to knowledge. This is the Pathfinder, and always I was getting confused if it's knowledge to data or data to knowledge, and in reality I realized that always is data to knowledge and then back to data again, hence the bracket. We're going to discuss about three things today. One will be about automatization and workflows. This is practically what Federica will tell us, and let's hope not like in the cartoon at the top. Then we'll speak a little bit about the data, and then somewhere in between about the machine learning. Okay, so when we started this Pathfinder, initially we were thinking in terms of machine learning with a very specific application, machine learning interatomic potentials infrastructure for that. Okay, so now, of course, this is not work done by me, and who are the people who are working on it? If you ask AI, you get the first row. If you ask the ACD organogram, you get the bottom one, is myself, who's leading the Pathfinder, Elliot, who unfortunately cannot join us, and Federica, who is next to me and will speak in the second part. Okay, so you already have the caveat of AI. You have to be very careful of what you ask and how much you can trust it. I suspect I don't have to spend too much time on explaining what PSDI is about. It's about physical sciences data infrastructure, and is trying to get into getting together quite a few, let's say, entities from institutes and facilities, national research facilities, then communities, computational initiatives. Practically, this is where myself is coming from, and of course, the big research institution groups and the laboratories on the experimental side. As I said, probably all the audience knows what PSDI is here, so I'll not insist on this. What was the aim of and what is the aim of the Pathfinder was when we started from the idea that in the machine learning already a few years ago for the interatomic potentials was a big variety of approaches. In general, all of them were using the same type of data, usually atomic coordinates, forces, and few other properties. But then how they were dealing with it resulted in a lot of potentials. So here you see the tree of potentials, which morphed since then. There is a newer version with more branches. The aim of the Pathfinder was to design and deploy hardware infrastructure to host both training data for machine learning interatomic potentials and the potentials themselves. As features, we want to be able to create, store, distribute, and interrogate the machine learning potentials and their training data, visualization and training workflows, benchmarking and validation. And here, when I say benchmarking, I'm not referring as typical HPC benchmarking, where people try to see how fast things are. We are looking at how accurate the things are and how valid are for scientific application. Ideally, HPC integration. And ideally, this was something that when we started looked like a very good thing and something very easy to be done. Since then, probably you heard, we had quite a few hacks around the world, and the HPC infrastructure started to put the walls up and very thick. So that seems to be a challenge that was will be quite difficult to pass. Now, before being close to Christmas, I will not give you a Christmas lecture, but I will give you a little bit of the history of interatomic potentials. So first potential that appeared about corpuscles interacting with each other, it's in Newton's Principia. So it's not the famous gravitation, it's a different type of potential. If you remember your Latin, probably you can read in there, and then tells you that two corpuscles interact with something which is 1 over r power n. Then there is another book around 1745, Bošković force curve, where you can see already, if you are into the field, you can see the curve which everybody knows these days. Gustav Mie came out with what is called the NM potential, 1903. And then Edgar Grunesen came out with another type of the potential, which is A over Rx, which is practically the same as Gustav Mie, but just a little bit simplified. Then what everybody knows in the interatomic potential world is the Lennard-Jones potential, which it was practically more or less the same form as Mie and Grunesen. And all these parameters that you see in these potentials were fitted to data. A lot of them were fitted to data from X-ray and other experiments that people were trying to do. Some of the terms over the time, people had good theoretical fundaments to derive them. So, for example, 1 over R6 became quite well established by London in the potential. But then, for quite a long time, the 12 term, for example, was fitted. There is a paper by Fowler Bernal in 1933 were trying to explain something about the structure of water, and then his first paper where I found that n equal 12 was put there. Lennard-Jones used to find the optimum around 11.4 in his papers, and still was a debate which value of n should be used. Okay, and this was long before any simulations. Okay, so people were still trying to use them. Then in the world of simulations, people started to use what is called the Lennard-Jones potential. Then they discovered that form, analytical form that existed, was not good enough to get the interaction between atoms. And what followed, a purgatorium, how I call it, where people try to modify the Lennard-Jones potential with all kinds of extra terms, some of them empirical, some of them more theoretical, but in general, they were trying to fix a problem that they knew that they have. And this lasted until mid 2015, something like that, until a new type of potential came out. And these are what is called the machine-learned interatomic potentials. I put it here just the equations. I'm not planning I'm not hoping you to understand them or to derive them immediately, but I put them here just to show you that while these machine-learned interatomic potentials, they have the machine learning into them, there is no black magic. There are well-defined set of equations that get into the calculation of the energy, and because they are analytical and time derivable, you can compute the force. There are two things important into this machine learning interatomic potentials. One is the fact that we know that using, in this case, a neural network, the mathematicians told that we can approximate very complex potential energy surfaces. So practically, we do not have the limitations that we had in the past with Lennard-Jones and variations of Lennard-Jones, that the analytical form was not good enough to capture the interaction. The other thing, what computer scientists did very well for us, first was the mathematicians, and second, the computer scientists. With the advance of neural networks in the last 20 years, they came out with very, very good algorithms to be able to fit these potentials to data. Why? Because if you look here and fast, you will realize that very easily you can end up with tens of thousands, millions of parameters to fit a very complex interatomic surface. Okay. But now we have two problems solved, but we didn't solve the problem of data. So now we know that we have the mathematics tells us that the analytic form is good. We have the computer science giving us the tools to fit. What we are missing now in this equation is data, and we need to have very good quality data in order to make these potentials to work. And this is what the aim of the Pathfinder, in a way, it is to help to get scientists to have this data. So, workflows. So there are two views of the world when it comes to workflows. You have the AI community, that they are very well. This is a picture from 1DB, one of the providers in the AI community. And they have a very clear idea about the integration with machine learning libraries and repos of data, a training environment, an inference environment, workflow orchestrations, and everything is very well. And then if you are a physicist like me, you look at them, and I can bet majority of them you have no idea what they are. I suspect the workflows that you are using have nothing to do with what AI community or computer science community is using. And then you go to the material science, the community where I'm coming from, and the world is totally different. Okay, so there is a little bit of overlap, but usually the focus is totally on other parts of the problem, even if everybody is trying to use exactly the same to reach the same goal. So practically, from the materials world, you have the workflows. There are quite few of them. You will be surprised to see that none of them is what the AI community is using. Some of them are better than others, some of them more advanced than others. For our purpose, and we are using AIDA, and Federica will tell later about it. But what is the main complication in material science, and the main focus is in general the training. How you get your data, how you generate your data, how you create the right features, how you train, and then the scientific application. A typical workflow, it goes practically from data generation, featureization, training, you test it, and then you realize that it's not good enough, and you do some active or hyperactive learning loop, and you go back to data generation and you redo the process. Now, depending what type of potential you are using, what machine learning model you are using to describe your system, this cycle can be very long and painful, or can be shorter. In general, if you start with very good data, the cycle is very short. So where do you get the data from? So at the moment, at least in the material science world, you have quite few sources of data. You can go to NIST, it's a good example, for example, and they have very specialized data sets and databases, and you can go and see where, if they have anything for you, and you can pull it. There is another project, you can see it here on the left. Right. OpenKim is called. They are very good in the world of classical potentials and having data from simulations. And it's a very good starting point. Then, if you go to MolSSI, they have a machine learning dataset repository, not for interatomic potentials, but for more data analytics. But you will discover that if you go to the website, you can download files. Okay, so a lot of tight things like identifying the data, metadata, and things like that are quite missing. And this is a recent paper published in November 2023 from Google, and you will, from their materials discovery project, and you will discover that they dumped all their data on GitHub. So the sources where the data is quite varied, and how you interact with them, the quality of the data is quite varied. So you have to be very careful. The other project that I didn't speak about in the previous one is materials project, practically one of the biggest in terms of data. Is very much concentrated of certain data from density functional theory. Practically majority of their data is coming from there. It has a very nice interface where you can search things and you can download information about your favorite element if it exists. There are, I think at the moment, they surpassed 1.5 million structures in one and for molecules similar things. They have a API, so you can usually integrate it in a workflow. I cannot say more about this, but people used this data when the data collection started here for analytics purposes, for machine learning, people started using it to train machine learning interatomic potentials. Actually, the Google paper uses a subset of this, and there are a few other papers using it and a few others coming. So this is a story of success, how data, which was kept in a certain amount of order and consistency, could be used and reused with a certain degree of success for generating machine learning interatomic potentials. What are the issues here? If you are trying to search across multiple data sets, since the things were designed not with interatomic potential in mind, but more with data analytics, things are not so nice and clear, and then probably not very fast either when you have to deal with millions and millions of atoms, structures. So now we go into the database. So the database part is the part that Elliot is working on. So we are trying to, and we are developing at the moment a proof of concept database and app, which will be installable centrally in PSDI, but users can get it and deploy their own. Okay. Users should be able to both interrogate, download and deposit data into the database and go across various data sets. Is not database, a standard structured database like you'll find for more standard machine learning applications, mainly because different data sets may contain less or more information. So you have to be very flexible in what users can do and what they can interrogate, because you may find structures which are interesting, even if they do not contain the properties that you are interested. It doesn't matter. You just build your own data set and you will recompute that calculations. You will augment your data set. We'll like to have an API, both Python and web interface. People can interact in an easy way or in a more automatic way. One of the issues that we identified very early, because somebody in Cambridge already started doing it in a Gabor's group, using normal database engines like Mongo, the search features were quite slow once the amount of data is big into the data set. So then one of the first tasks that we had was to put opensearch into it to replace the normal searching. Of course, you need to integrate it in the workflow, and the important bit is to be reproducible and reusable. Okay, so for reproducibility, we have each set has a standard metadata, which is a metadata invented by us, but the plan is to integrate it with the metadata of PSDI. So then the specific metadata to come on top of the PSDI metadata. So the proof of concept, we do it in collaboration with Gabor's group in the University of Cambridge. So from the technical point of view, the data in general, you can provide it as a JSON dictionary. and contains basic stuff for material science, like elements, positions, energies, forces, stress, dipole moments. You can put whatever properties you want for your application. Metadata, units, provenance, and as I said, we can have user-specified keys that you can explicitly annotate your data with whatever you think it's useful. So at the moment, there is an API access via Python client and command line. It's complex. You can do complex and scalable queries via opensearch. So practically, once we replace the old Mongo search that existed with the opensearch, the speed up was 100 times for the tests that we tested. One thing that it's important, you have to have a data discovery feature, because the data is unstructured. You are never able to know what is inside your data. So you have to offer an interface which is quite intuitive and useful and fast for users to be able to download, to search, and then create, discover what is inside the data set. And there are quite a few things, list and frequencies of keys that were in the database, visualization functions. This the visualization work in Jupyter Notebook at the moment. The list and frequencies, you can do them both in Jupyter Notebook and command line arguments. So the important thing is to be able to filter data, and this you can do to train new ML models, and then to be able to generate the new structures and the machine learn to force field themselves in the same database. Okay, so here on the left we have a diagram of the hydra of how we're supposed to interact with the database. In general, when we decided to go this route, the planning was that the database can be integrated in any workflow manager. We will not go the route where we develop a workflow manager and the database is central to the workflow manager. So the database is central and the workflow manager can be wherever you want. We give you the Python and you'll be able to integrate it wherever you want. Same for the machine learning model. The database is agnostic, doesn't know any machine learning model. You can integrate it with whatever machine learning model you want. We are playing at the moment with a maze, and we played with neural networks, high-dimensional neural networks, but that doesn't mean that we, in the future, will not look at other models. Now, an example, how good are these machine learning models? Because at the end of the day, why do we do this? We do this because we can do better science, and we can do so. This is an old example. We spent quite a lot of time in Elliot and a few others to trying to develop neural network potential for a metal organic framework. This is a nice molecule, very good for various applications, from catalysis to CO2 absorption and few hydrogen storage and few other things. I mean, there are a long list of applications who are more interesting. And what we find out that if we train the model against DFT data, after a few iterations in the loop that you saw earlier, we can get quite good accuracy. Okay, and that's important because if you want to do DFT or more, the systems tend to have like at least 100 atoms in the smaller one, but more normal it's like 400 to 1000 atoms. So DFT will not be able to give you too many of these calculations. You will have to spend quite a lot of time. So the machine learning, you can see it's reproducing very well the DFT data, and the structural data is reproduced quite well with relatively small errors. Then, after we created around 2000 structures we needed to train this model, time moved, and Mace model was published last year at one moment. And we said, okay, let's give it a try. Now the luck was, because we had a lot of good quality data, we didn't have to do any. We just took our data and we trained it to Mace, and after a few hours we came out with a potential that you can see it reproduces quite well the data. The trick here is that because the way in which the training was done at the moment, we couldn't use all the 2000 configurations, so we had to use only half of them because we were not fitting in the GPU. At the time, we could train only on one GPU. But despite that, the result is very, very good. So since then, people understood that this model is very data efficient. So, but the key was that the data was there, was curated. We knew that we can trust it and we can use it for this purpose. And while it took us more than 6 months to come out with the previous potential, this one, it came out in one afternoon. But, so since Mace was released, there were other potentials released, and then we are going back to the materials project. People discovered the materials project has a lot of data about all kinds of random systems. And what they did, they took out that data and they trained different machine learning models. And here, if you go back to the website down, you can see various machine learning models, how well they perform against this training set and how well are able to predict. And the Mace at the moment is one of the best performing. These are, let's say, if you go on the website, you will see the public ones, open source models. There are proprietary models that people are developing at the moment, people like Google and a few other specialized companies. So there is a very, very hot race and research going on in the area, and everything goes around data and being able to access it. Okay, so this is all from me for the moment. I suspect there are no questions, we don't see anything. So then we will change the chairs. Physically change the chairs, and Federica will take over and tell you more about AIida, the workflow that we are using.
Okay. So first of all, what's AIida for who doesn't know AIida? It's a Python infrastructure that is one of the most used to handle workflows in computational sciences. So you need to run a calculation with any software, not any, but it's made for many software. And you can use AIida to handle the process, to automate and manage the data. And also it's very useful because it helps with reproducibility, because you can share it. For example, when you publish your results, you can share the workflow that you use to do the calculations, and people can easily use the workflow and reproduce exactly the same data. Here is the documentation. No, you don't see, you see the cursor, okay? If anyone wants to have a look when we send the slides. And you can interact with AIida in different ways. So there is AIida Lab, which is a user-friendly interface that has some official deployments, but also you can deploy your own, so you can make it personal. And then there is the command line. There is this Verdi command that allows you to interact with the database and with all the processes and the nodes in which AIida stores the data. So, for example, this is just an example of a command. You just write Verdi process. Process is the command that handles any process that you want to run in AIida. And list just says, okay, show me what's going on at this moment. And this is the output. So you get a list of every process that is going on, where the process is stored. These are the AIDA nodes. What the process is doing and how the processes are connected to each other. There are, of course, a lot of other commands that you just learn while you use AIDA. And also AIDA works with plugins. So there is a AIDA core plugin that handles the basic things that are common to most computational science software and calculations in general. But there are a lot of different plugins to handle specific software or type of data. For example, maybe you have heard AIDA about, because Pathfinder 4 is working on GROMACS plugin. I'm using the Quantum Espresso plugin a lot. So that's for running Quantum Espresso and run DFT calculations. Or for example, the pseudo plugin, it's a data type of plugin that handles the pseudo potentials that are used for creating the inputs of the DFT calculations. And these are just some other examples of plugins. So, okay, so another functionality that is important in AIDA is that is data provenance. So you can keep track of all your data and where everything comes from. So this is barely readable, but this is a graph of all the data that I used and produced in geometry optimization calculation. Basically, the green blocks are the data type, the data nodes. So they store, for example, the structure. So I have an input structure with some information, some parameters, the pseudo potentials, and they're stored in some specific nodes. And then the orange and pink boxes, they are processes. So they are some specific workflows that I submit for geometry optimization and other things. Like in this case, I submit the geometry optimization. Here things happen because I had some error, so automatically it handles the error. And then it goes here where I do another type, I do a single point calculation. So you can see this is a lot of data, and it's important to keep track of it because it makes it easy, very easy to reproduce the same process. So as I said already, reproducibility is an important part of the purpose of AIDA. And it allows to handle your workflows in a better way than you would do just manually. So with AIDA, so as I said also in the beginning, AIDA helps with automating processes. There are already some workflows in the plugins that are already written and ready to use. But you can also make your own workflows or connect different workflows. So in particular, there is the workchain class in AIDA that is implemented to store all the data relative to those calculations and don't lose track of the data provenance. So basically, the things I just showed in the graph before, they can be printed out because every step of the workflow is saved in the nodes in AIDA as part of the workchain class. So this workflow here, this is an example of what I'm doing. In this one, I get an initial geometry I work on MOFs, metal organic frameworks at the moment, but of course you can do it for everything. I get the initial geometry in the form of a zip file. I optimize it. If it works, I run a single point calculation. And then in my specific case, I did phonon calculations and other calculations. And then I want to store the results. So this little workflow here, it's already using AIDA Quantum Espresso plugin, PhonoP plugin, and Butter plugin. And while they already have many workflows implemented, I still needed to, in some cases, to write my own to just make exactly what I want. So in some cases, I need to write some new work chains. In some cases, I just need to modify and customize a little bit what's already there. And then I need to connect everything. Specifically, what we want to do as a big picture thing is actually this should be all connected with the database we are working on. And maybe you can also do other calculations, not only the phonons and other charge. You can produce a lot of data, and then everything is stored in the database and can be used for machine learning. So ideally, a machine learning plugin would put all this together and use the results to produce new data or to study the data that we have. Because in the end, the final aim is to have a workflow that just does everything, puts everything together, and then outputs data ready for analysis and publication. So the point is that you can focus on just the science, increasing productivity rather than doing things manually or like spend a lot of time focusing on how to make the calculations go. So as I said, an important thing is that you can create the work chains or just modify a little bit what you already have. So everything that's already written in AIDA can be customized however you want. There are some default values, but for example, I had to change, when I did the geometry optimization that I talked about, I wanted to change some parameters. So I can easily just rewrite a small Python script for submission and just customize it to, for example, to change the functional or the spin. Like these are in the script here are just some examples. But yeah, basically you can do whatever you want with your data. And this is very useful if you need to maybe run the same calculation, but change just one parameter. You just rerun it like this, and the rest stays the same. And another important thing that I also mentioned is that you want to connect your data with a database. So there are already ways to connect AIDA to database like materials project. So there are some Verdi commands, Verdi archive that allows you to get data from a database or deposit data. You can, like ideally we would like to connect it to our own database, and as I said, just have everything connected, the database, the workflow for the calculations, and machine learning, and again, creating new data and new calculations. So I don't know if someone told. No, it's not touch. Okay. Anyway, I'm almost done. So this is another example of something we want to do. So in my PhD, I did some high throughput screening calculations on MOFs. So in AIDA, you can do high throughput screening calculations. So have a lot of data and run different type of calculations on this big set of data. So what I did here was that I got all these materials. I had all the single zip files for the MOFs, and I ran DFT calculations on 2 different levels of theory to get the bandgap value. When I did this, I didn't know any better, so I did write my own script to automate. I did some things manually. I downloaded all the zip files, and I have just my data stored very randomly, a little bit in the zip files, a little bit in Excel files, stuff like that. Obviously, using AIDA, something like this could be done very easily. You can easily run high throughput screening calculations with ready-made workflows. If you need to get the files from a database rather than downloading manually everything, you can connect to a database and then deposit in another database. And also, as I said, I did the calculation in 2 levels of theory. So some calculations are more precise than others. But the thing is that in general, in many databases, there are already, like in the materials project, for example, the Alin mentioned, the data is calculated with not very precise methods because they are those that are less computationally expensive. But for example, you could just run, submit a AIDA workflow and redo all the calculations with different functionals, different methods, just by changing one parameter and keeping the rest all the same. And that would make it very easily. So yeah, something like this, a throughput screening process and workflow would be very nice also to then obtain all the data and use them for machine learning. And yeah, that's it for me. So if you have any questions.
So I think we should stop the thing. See, there was a question that I answered already.
Okay.
Let me exit full screen. Okay. Ah, no, that was yours.
Okay, yeah,
sorry.
should I close the screen? Yeah. Do you want to go back here?
So we had a question about, there is another question, if you can read it.
Your scoring of accuracy as a percentage, since one can never know the true value, measurement errors prevented, then what are you comparing against?
So are you referring to the accuracy from the machine learning leaderboard, I suspect. So I think I can let you speak, no? I don't know. Nikolai is in charge.
I mean,
so
you can do if they are willing to.
Yeah.
If not, they should. So they've commented the same that you had a slide showing some percentages.
Oh yeah. So I suspect that's what you refer. So the accuracy is with respect to the DFT data. So the aim of that project is to benchmark how good these very complex analytical forms are to approximate this complex free energy surface. Okay, so it's not with respect to experiment. So it's really how well we can fit that with these potentials. That so unfortunately, a lot of people in machine learning stopped at that. So we never really benchmark against physical systems. Yeah. Yes, exactly. That's the thing. So now we are working on benchmarking the science of these potentials, and you have to keep an eye. Results soon will come out. How do you secure the reproducibility of your results? Do you save the process in a particular way? How can data provenance be accessed? So I think Federica can answer this one.
So for the data provenance first, it's just you're referring to the AIDA data provenance that I show, I guess. It's just some Verdi commands that just allow you to create that graph and just see what's going on. You can make it also more, that one graph that I showed, it had a lot of information. You could also have less information. Also, when you, there are Verdi commands to handle basically everything. So when you see the process, you can have more insight on the processes and see what every process creates, and just have it print out and read it. And And about the reproducibility of the results, I don't know exactly. I mean, the fact that I can just rerun always the same calculations in the same way is the way that I mean to ensure reproducibility. I'm not sure that I got the question now.
I mean, everything is recorded into the database, so practically VerdiRun can replay anytime the same script, and you are sure that the things will be processed in the same way, Leandro. So this is you just get our work chain and you just VerdiRun, given that you have the hardware resources available. So practically you can run it on a different computer, maybe even with a different version of the software. Of course, we assume that the software is perfect and the computer is perfect and they give you the same results. But it is the reproducibility of the workflow, okay? So that's always reproducible. Now, ideally, you would like even the calculation to be reproduced, the numbers, but that depends on the software and the hardware that you are using. What is the structure of the data in your database? When I spoke earlier in the year, you're using binary blobs, which are absolutely not useful as blobs, so must have some kind of internal structure. Yeah, so there are two kinds of structures. So there is a rigid structure that practically what I call it the PSDI metadata structure, which should be rigid and you should provide. And then there is a lot of structure that comes from the materials that simulations that you are doing. Okay, so will be the blobs that I was referring are practically the input files, the output files, the log. Not so you do not save intermediate outputs which are huge. Okay, so you really save text files. Another thing which you will have in AIDA, for example, will be the script that you use to submit the calculation to the queue. So you have that one too. Then you have another part which is normal, easy. For the machine learning will be, like atom names, positions, forces, stresses, which are just numbers. Okay, so tables of numbers, then other properties, which again are just numbers. Is the provenance data saved in a JSON, for instance? So the provenance is the node. So there is a command, like you saw in the example that Federica showed to you, that you can export all that and you can get. Now I do not know what format exports.
I do not know actually, because I've always just used it to follow a process I was running, so I didn't need it.
So, but being Python, usually everything comes as a dictionary. In AIDA, everything is a dictionary, so you can save it wherever you want. You serialize it. Do you also need to export the tools, or are they stored in public repositories? Okay, the tools. These are okay. So there are various type of tools. Okay, so will be the tool which is the code, which needs to be installed. So you do not store the binary of the code. You just store the information about on which cluster you run your calculation and which modules you used and which binary you used. So you store that information, but not the binary. And the other part of the tools you are meaning is the workflow itself. The workflow is a tool. And that one, you can store it yourself wherever you need to store. So AIDA will not store that for you. We'll store all the operations that the workflow does, but we will not store the workflow as far as I know. And you can push it wherever you want. So I think AIDA uses GitHub to store their workflows, for example, and via various plugins make it public like that. Where the workflow metadata and produced actual data are stored, and who does access to either or both of them? A cloud with some form of authorization process. Okay, so if you go to the website that Federica kindly put on the websites, you see that you deploy the AIDA, you can deploy the AIDA yourself. And all the user access, it's managed by you. And the database stores the metadata of the workflow and the produced results in that database. So you can have it on your premise. Do you want to set it up in a cloud? And this is what we are planning to do. This will be one of the deliverables of PSDI, to have an AIDA instance in the cloud that you can use for your group and things like that. That's user management that AIDA allows you to do it, but then is the job of whoever commissions such a database. I see no more questions.
Did you just want to potentially answer the very first question?
Okay, I'll answer it live. Okay, so first one, how long does it take to create a new workflow with AIDA and then modify it for another case? Okay, so now how long is a piece of string? Depends very much of how good you are with writing Python. So when I wrote my first one few years back, before a lot of workflows were available, the geometry optimization, I could run it in quite less than 1 hour without documenting it. So it's quite, depends how good you are with Python and how good you understand the framework. Some modifications are relatively simple. I don't know, Federica did quite few. The extension of the geometry optimization was quite fast.
Yeah, because that already has, like, the original workflow already has a lot, so they could be easy. But if you need to create a new work chain, yeah, I guess that very much depends on you studying how the work chain works in AIDA and how good you are with Python. But then if you get it, like the next steps, they should be quite easy. It's just maybe the first time you do it, it's a little bit. By using a ready-made workflow, it's quite easy. Yes. And also modify small things, I would say.
So I want to say a massive thank you to Alin and Federica for coming along today and presenting their work. Obviously, if you do want to follow up some more with them, please do get in contact with them or the rest of the PSDI team about any of the other work that was kind of mentioned in some of the other work that we're going on. So you can get some more information about what we're doing on our events page on our website. You can also find us on social media. So we're on, I guess, X or Twitter, and also on LinkedIn. And the webinars and some of the previous webinars recordings do go up on our YouTube channel. If anybody else you think might be interested and wasn't able to make it to any of the webinars today. And some of the best way to follow up on some of what we're doing, if you're not regularly on social media, is to join our JISC mail mailing list. And so that's easily accessible from the footer of our website. We don't bombard you with emails. It's usually only sort of about upcoming webinars or a little highlight on what's been going on within the project. So thank you all for joining us today, and thank you very much again to Alin and Federica.